So in this first lecture, we'll discuss a bit about probability. We'll try to get a notion of it, and we'll also define some related concepts. So the first point which I should mention is the approach that we'll follow will be the frequentist approach. So traditionally, there are two schools of thought with respect to how the concept of probability is defined or understood. So we'll focus primarily on the first of those, is the frequentist approach. And as the name suggests, this is more concerned with frequencies of the occurrences of certain events. So in probability, we usually we discuss in terms of experiments, outcomes, and so on. So let's say we have a given experiment which has a certain number of outcomes or events. Now, some examples could be, let's say if we roll a dice. So this is our experiment, and what face comes on top can define my outcome or event. So in this case, we have 6 possible outcomes. Where the top face could be 1, 2, 3, 4, 5, or 6. Now let's try to get a notion of what we mean by probability. So if we repeat an identical experiment n number of times, and we observe that the event EI occurs Ni times, then we can define the probability of EI, which we'll denote as P of EI, as the limit of Ni over n as capital N tends to infinity. So basically, what is the fraction of times EI occurs if we repeat the experiment for a very large number of times? Now, probability should satisfy some properties. So we'll need to define some axioms. And before defining the axioms, let me mention that the set of all possible outcomes for any experiment, we'll refer to that using this symbol capital Omega. So now coming back to the axioms, the first one should be probability of capital Omega equals 1, which means something must happen out of all possible outcomes, or in other words, the experiment must have an outcome. Second one is, for any event E, the probability should be greater than or equal to 0. So either this event happens or it does not happen, where E belongs to the set of all possible outcomes. Now next, Basically, for any disjoint EI belonging to the complete set, this equality, that is the probability of the occurrence of the union of these disjoint sets, should be equal to the sum of the probabilities of these individual events. And this is known as the axiom of countable additivity. Now, it is straightforward to see that these axioms lead to the following theorems. The first is the probability of the occurrence of an event is 1 minus the probability of the non-occurrence of the event. So here EC refers to the complement of E. So if we can write sigma as the sum of E and EC, and E and EC are disjoint. In set theoretic language, EC is the set complement of E. Now we have seen that the probability of getting some outcome is 1, that is P of sigma is 1. Now E is some subset of sigma. So its probability should be less than or equal to 1. So this can be 1. This becomes an equality when E, the event E, refers to the all possible outcomes, the set of all possible outcomes. In every other case, this probability is less than 1. The next is P of an empty set or null set is 0. What basically means is that when we do an experiment, the probability of nothing happening is 0. So we'll get some outcome. Next, if E1 and E2 are subsets of capital omega and not necessarily disjoint, then the probability of the union of E1 and E2 equals the probability of E1 plus probability of E2 minus the probability of the intersection of E1 and E2. So this is easy to see from set theoretic ideas as well, that if you look at it in terms of Venn diagrams. So this is the complete set omega, and we have these two sets, E1 and E2. So when we add the probabilities of E1 and E2, there is a double counting of this region. That's why we subtract that when we look at the probability of the union of the two events. Okay. So for most of our discussion, we will restrict ourselves to experiments where the outcomes are described by one or more real numbers. We'll denote these numbers as xi. Now, the repetition of the experiment need not always give the same outcome. Now, this could be due to an inability to reproduce exactly the initial conditions, or due to the probabilistic nature of the process under study. Now, these xi's will be known as, or will be referred to as, random variables. That is, these are variables whose values cannot be predicted exactly. Now, the set of all possible values of xi for an experiment and define its sample space. And this sample space is similar to what we were discussing earlier, the set of all possible outcomes. So sample space is usually denoted by this capital omega. Now, this random variable, it could be discrete. So in such a case, the sample space is a set of discrete points. And if we look at some examples, one could be the classical case of throwing a dice, and we see what face comes up at top. The other could be the age of students in a classroom. On the other hand, if the random variable takes continuous values, so then the sample space is an interval on the real line, or sets of intervals. Some examples could be the frequency of radiation from a black body, the angle at which an electron is emitted from an atom in beta decay, or if we look at, instead of looking at the age of the students, if we look at the height of the students in a classroom. In some cases, the random variable could be a combination of these two as well. So, let us develop our language for our discussion. So, we'll say that an experiment results in an outcome. And this outcome for our current discussion would be a set of real numbers. They are random variables. Now, these random variables, they form what is known as a sampling of a given parent population. Now, the differences between sample space and population are important. So, population is a list of all members. Some of these members may be identical. Sample space, on the other hand, is a set of all possible results of an experiment. only one member of the set at a time represents identical results. Lastly, sample is a list of the results of a particular experiment. Some of these results may be identical. So how often a particular result, that is a member of the sample space, occurs in the sample should be approximately proportional to how often that result occurs in the population. So members of the population are equiprobable. Whereas members of the sample space are not necessarily equiprobable. The sample reflects the population which is derived from the sample space according to some probability distribution, usually called the parent or the underlying probability distribution. So this takes us to a discussion of probability density functions. Also abbreviated as PDFs. So we'll try to understand this with some examples first. So again, return to the classic example of throwing a die. Now I must mention that unless specified otherwise, by a die we refer to a six-sided die. Now throwing a die, we can write the sample space is consisting of these 6 numbers. Now if you look at the probability distribution, and the probability of, unless the die is not biased in some way, the probability distribution is simply described as probability of getting a 1 equals probability of getting a 2 equals probability of getting a 3, and so on. So there is a 1 by 6 probability of getting any one of these numbers. And this gives a parent population of 1, 2, 3, 4, 5, 6. But on the other hand, if we consider throwing a die where one side is marked as 1, 2 sides are marked as 2, and 3 sides are marked as 3. Then the sample space consists only of the numbers 1, 2, and 3, and the probabilities are probability of getting a 1 is 1 by 6, probability of getting a 2 is 2 by 6 or 1 by 3. The probability of getting a 3 is 1 by 2. And the parent population is in the discrete case, we have a probability function filtered out by fx, which is greater than 0 for each value of x in capital Omega. From the axioms of probability, the sum of all those should equal 1. So if A is a subset of omega, probability of observing that event is described as the probability of getting a random variable which belongs to A and which is the sum over all the fx's corresponding to elements of A. Now I must also mention that for discrete cases, the probability density function is also referred to as the probability mass function. Now for continuous random variables, so the possibility of or the probability of getting an exact value is 0 because the total number of possibilities is infinity. So it makes sense to talk only of the probability of that the outcome will lie in a certain interval. That is, we speak about this probability that my random variable lies between x and x plus dx, where dx is infinitesimally small. And this is described in terms of the probability density function. And the summation, which we had in the discrete case, basically turns into an integration. Now, one associated quantity to the probability distribution function is the cumulative distribution function. Which is abbreviated as CDF. So the cumulative distribution function is the probability that the value of a random variable will be less than or equal to a given value. So, instead of the integration over the entire sample space, or in case of, or let's say from minus infinity to infinity, instead of that, the integration is from minus infinity up to some x over this probability density function, and this will describe my cumulative distribution function. It's the probability that my random variable has a value less than or equal to a given x. Now it's easy to see that at the end point, the cumulative distribution function gives either a 0 or a 1. So there is a 0 probability that the random variable takes a value less than or equal to minus infinity, and there is an getting a probability, or the random variable obtaining a value less than or equal to positive infinity is absolute. So the probability is 1 in that case. So if we examine the properties of the CDF, again, just like probabilities of certain events, the cumulative distribution function should also lie between 0 and 1. It should be a monotonically increasing function, because as we span the space of these real numbers, the probabilities keep getting added as we increase the interval, basically. Now if we look at the probability of the random variable lying between two values or two numbers, that can be described by the difference of the cumulative distribution functions defined at those 2 points. Now if fx is discontinuous, at x, that would mean the probability of the random variable assuming the value x is given by the size of the jump at that point. And if the cumulative distribution function stays continuous at a given x, then that would imply that probability of the random variable assuming that value is 0, which again falls back to the idea that since there are an infinite number of points, the probability of being at a single point is 0. Now it can be noted that the cumulative distribution function is more fundamental than a probability distribution function, because the cumulative distribution function is an actual probability rather than a probability density. Now, if we know the cumulative distribution function, we can derive the probability density function using the following relation. So we can describe the observations in terms of both probability density function as well as the cumulative density function. So next we can introduce some concepts like expectation values. So if we consider a single valued function ux for the random variable x for which the probability density function is given as f of x. The expectation value of u of x is denoted by u of ux. It's defined as this integration from minus infinity to infinity of u of x times f of x dx. And as we have seen, probability density function can be related to the cumulative distribution function. So for continuous fx, this can also be written in terms of the differential of the cumulative distribution function. If you look at the properties of the expectation value, if k denotes some constant, then the expectation value of the constant is the constant itself, which is easy to see. Because left hand side becomes and this last integral is nothing but 1. Now building on this, if k is a constant and u is a function of x, then the expectation value of k times u is actually k times the expectation value of u. And lastly, if k1 and k2 are two constants and u1 and u2 are functions of x, then the expectation value of the linear combination of u1 and u2, defined like this, is the same as linear combination of the expectation values of u1 and u2. So that is E is a linear operator. Now just a comment on popularly used notation. So in a lot of literature, instead of writing E of u of x, simpler notation, u of x is u of x sandwiched between these angle brackets is also used. But this is mostly inspired from quantum mechanics and Bra-Ket algebra of Dirac. Now, from expectation values, next we move on to moments. So moments are certain special expectation values. So the mth moment is defined as the expectation value of x to the power m. So if the moment is finite, then we say that the moment exists. The most commonly used moment is the mean, which is nothing but the first moment. A mean is a measure of locations. So usually it can give a good idea of where the most probable region is. So if you have a distribution like this, then the most probable region is the region around mean. But this is not always true. So for example, if we have a distribution of this kind of a shape, the mean is in fact not a good indication of the most probable region. Additionally, we can also define what are known as central moments, and these are moments about the mean. So the nth central moment is defined as x minus mu to the power m, the expectation value of x minus mu to the power m, which is computed using this integral. If the mean is finite, then the first central moment is clearly 0. In fact, if the probability distribution function is symmetric about the mean, then all odd central moments are 0. A quantity which is of great interest is the second central moment, which is also referred to as the variance. So it is denoted by v of x sigma x square, or just sigma square. So we can write sigma of x square equals e of x minus mu whole square. With some simplification, this can be shown to be the difference of the second moment and the square of the mean. And another relevant quantity is the standard deviation, which is equal to the square root of the variance. So that was the motivation behind defining the variance as sigma square. So you can write sigma for the standard deviation. And standard deviation is a measure of the spread of the probability distribution function about its mean. Now, as we mentioned previously, symmetrical distributions have the odd central moments to be 0. So therefore, in general, the odd central moments provide a measure of the asymmetry. So if you look at the third central moment and make it dimensionless. This is usually done by dividing it by sigma cube. Then this gives us a quantity known as skewness. It's the most common definition used. Well, this is also known as the Fisher definition of skewness. It must be mentioned that there are other definitions. For example, there is Pearson skewness, which is just the square of the Fisher skewness. Now, another feature of the probability distribution function, which can be estimated based on the moments, is how sharp the peak is. And this is defined using a quantity known as kurtosis, which is a function of the fourth moment or fourth central moment about the mean. So again, there are different definitions. So if you look at the Pearson kurtosis, the definition is just expectation value of the fourth central moment divided by sigma to the power 4. Alternatively, there is this Fisher definition, which is simply beta 2 minus 3. Because of this minus 3, gamma 2 comes out to be 0 for Gaussian distributions. And that's why this is the popularly used definition. Now for a probability distribution function which has gamma 2 greater than 0, we call it leptokurtic, and when gamma 2 is negative, we call it platykurtic. These two basically describe whether the PDF is less or more peaked than a Gaussian, or whether they have higher or lower tails.